Hello student, welcome to today's session. So we are into the second session of topic of isomerism. In the first session we talked about the basic definition of isomerism and the classification, the basis of the classification of isomerism. So objective of today's session is we would like to touch the topic of isomerism by definition once again, and how is it being classified and what basically is there in the structural isomerism, and how this classification further get divided into chain, position, function, and metamerism, tautomerism, and ring chain isomerism. As I said in the previous session as well, that before we go into the discussion of structural isomerism, I just would want you to understand this topic of degree of unsaturation, because this is very very important, because with the understanding of this particular topic you are able to understand how the different number of structural isomers would be created and how they then get classified into different categories. So this particular session I already have uploaded in the, if you could see in the playlist of Balle Balle Organic series of class 11th, this particular degree of unsaturation or double bond equivalent or index of unsaturation or unsaturation index, all of these are synonyms to the same term, degree of unsaturation. So you can see into it, and it would open up your mind in many ways. It is very very important topic and you should know about it. Now let us go into the discussion once. Let's do it. Let's discuss it. Isomerism, if I have to define what do we mean by isomerism, if I just would define the existence of two or more molecules having same molecular formula. I just have wrote a molecular formula here, C2H6O, which could be available if I would go to the market to buy it. It would be available in two forms. One form is this, which we call it as ethanol or ethyl alcohol, and another one is dimethyl ether. Dimethyl ether, that's the common name, dimethyl ether, or methoxy methane is the IUPAC name. So these are the two ways it would be available in the market. So these two compounds would be said as to be isomers to each other. Now let us define the definition once again. What we have said, that two or more molecules having same molecular formula is same, but different bonding arrangement of atoms. The atoms are arranged in a different ways. Here two carbon attached to OH group, here carbon, oxygen, carbon. The bonding arrangement is different in two forms. When you have two or more molecules having different bonding arrangement, they basically would get classified into the category of structural isomers. They would be said as structural isomers. This we have said in the first session as well. And when the orientation of atoms are different in the space, they get classified under the category of stereoisomerism. So to have the understanding of stereoisomerism, I just would request you to see the session number 1 where I have explained it in length, or in the subsequent lecture wherever structural stereo would come after the structural, you are able to understand it well. So as I said in the first session as well, there is a tip to remember that when you are saying two isomers are structural isomers, their bonding arrangements are different, then definitely their IUPAC name would be different. IUPAC, they would have different IUPAC name. So structural isomers would have different IUPAC names. IUPAC names of the structural isomers are different. But as a matter of fact, for stereoisomers, when you say two compounds are stereoisomers, their IUPAC names are same IUPAC name. They would have same IUPAC name. So if you want to see into it, I just would say just see the session number 1. There I have explained this particular thing in length. Now coming back to the topic of structural isomers. So structural isomers, so the objective of today's session was to understand this, but before I go into that, I just would want to touch this for 5-7 minutes, degree of unsaturation. What does it mean? Now simply if I would write here a formula like, let's say C3H6. C3H6 would be available in two forms if I would draw it like this or this way. One is the open chain, another is the cyclic. And if I would just place one double bond here and place the hydrogens, you would get the formula comes out to be, just to keep the tetravalency of carbon intact, I just have added the required number of hydrogens onto this. And similarly here the carbon is attached to two bonds, so here two hydrogens and two hydrogens, so it becomes C3H6. Now in this particular case, if now I am explaining what do we conceptually mean by degree of unsaturation. Into this, if I just would add hydrogen here, if I just would add theoretically a pair of hydrogen atoms or a molecule of hydrogen into this particular compound, which we are saying it as propene, what do we get here? I shall be getting something of this nature. Already there was 3 hydrogens here, 1 hydrogen here and 2 hydrogens here. So you theoretically have added 2 hydrogen atoms or 1 molecule of hydrogen. So 1 hydrogen comes here, 1 hydrogen comes here. Now all the carbons are now having maximum number of hydrogen atoms and their tetravalency is complete, or simply I would write CH3, CH2, CH3. So what you have generated a alkane. Which alkane you have generated? This alkane is said as propene. Okay, fair enough. Now similarly, if I do the same thing here also on to the second molecule, which is cyclopropane, this compound is cyclopropane. Into the cyclopropane, if I would break this bond, let's say I just would break this bond, what do I get then? I just have broken the bond and the hydrogens are still intact. These hydrogens are still intact. Now since I have broken the bond, so the corner carbon atoms no longer remain tetravalent. To keep their tetravalency intact, I just have added 1 hydrogen on both sides. Now if you would carefully see, this is the same molecule. It is nothing but propane. So again you get a propane. So what do we mean by degree of unsaturation? So here comes the interesting point. So the degree of unsaturation for this particular compound, I will say 1. What does it mean? Because I added 1 molecule of hydrogen such that if I just would add 1 molecule of hydrogen to this compound, that is propene, it turn up to become alkane. And alkane is the entity in which more number of hydrogen cannot be added. This is the maximum hydrogenated compound. Is it okay? Alkane is the maximum hydrogenated compound. More hydrogens can never be added into it. Similarly, cyclopropane, if I would say cyclopropane, to cyclopropane, if I just would add 1 molecule of hydrogen, 1 pair of hydrogen atom, pair contains 2 hydrogen atoms, 1 pair of hydrogen atom, it tend to become a alkane, open chain alkane. So we will say the degree of unsaturation for this compound is also 1. Now what do we mean by degree of unsaturation then? Number of pair. So if somebody would ask us what is the meaning of degree of unsaturation, number of pair of hydrogen atoms or hydrogen molecules. The number of pair of hydrogen atoms or hydrogen molecules you theoretically added to any organic compound such that it either would turn up to become alkane or it either would turn up to become saturated open chain hydrocarbon, open chain saturated hydrocarbon. Then that number of pairs or that number of hydrogen molecules would be said as to be degree of unsaturation. I think I made my point clear. So this again can also be mathematically found, just like if we have wrote this formula C3H6. Now for this, if I have to find the degree of unsaturation, how can I do from the formula? 2 into number of carbon atoms. So 2 into number of carbon atoms. So carbon atoms are 3 here, plus 2. 2 is to be added then, and thereafter nitrogen is not in the formula. If the nitrogen atom is there in the formula, that has to be added. Hydrogens are to be subtracted. How many hydrogens are there? 6 hydrogens are there. And if there is any halogen, that also has to be subtracted. And if in the formula there is oxygen, so since this formula do not contain any oxygen atom while evaluating degree of unsaturation, so there is no need of oxygen while evaluating degree of unsaturation. So only thing which you have to recall is the number of halogen atoms. Number of halogen atoms you have to concentrate on, nitrogen atom, carbon atom and hydrogen atoms. So divided by 2, so the answer came out to be 1. So degree of unsaturation 1 means that this particular formula which we have already done either would have 1 pi bond, it would have either 1 pi bond or it would contain 1 ring. So as soon as you happen to see or happen to get the meaning of degree of unsaturation or from a given formula, from the say for example C3H6, I am able to understand that if there is a compound C3H6 as soon as C3H6, for this I have found the degree of unsaturation 1. This means the number of ways it would be available in the nature structurally. It could be in the form of double bond, or it can be in the form of ring. So that is why it is very important to understand degree of unsaturation before we go into the structural isomerism. Other way to do the same thing is that degree of unsaturation simply would mean the sum of number of pi bonds and rings in a given compound. Although this definition is deceptive, just see into the video which I have already said. See the discussion of cubane. There I have done it in very length, so please refer to that. But generally it is the sum of pi bonds or rings in a compound. When I say degree of unsaturation 0, it means there is 0 pi bond, there is no pi bond, and 0 ring, there is no ring also there in that compound. And when I say degree of unsaturation 1, that means it would have either 1 pi bond, or 1 ring. And if I say degree of unsaturation 2, that means it would have 2 pi bonds, or it would have 2 pi bonds, or 1 ring plus 1 pi bond. Or you can say it may also have 2 rings. So and so forth, and you can keep on adding like this. If degree of unsaturation 3, so it could have 3 pi bonds, 2 rings, 1 pi bond, or 1 ring, 2 pi bonds, or 3 rings, and so forth. So let me take one example here. Say for example, you are being given this C4H6. So degree of unsaturation would be, as per the formula, 2 into number of carbon atoms 4 plus 2 is to be added, and number of hydrogen atoms are to be subtracted, divided by 2. So degree of unsaturation 8, and 8 plus 2 10 minus 6 divided by 2 comes out to be 2. So degree of unsaturation is 2. So when the degree of unsaturation is 2, that means it would have 2 pi bonds. This particular compound would have 2 pi bonds, and 2 pi bonds can be available, 2 pi bonds, or you may also say it to have, if I just would write it here, it would have C4H6. Degree of unsaturation 2 means it can be available in 2 pi bonds. It may have 2 pi bonds, or 1 pi bond plus 1 ring. It can have this thing, or it can have 2 rings. The point here is very interesting. The point here is 2 pi bonds can be available in 2 carbon-carbon double bond, or 1 triple bond. Because I know for sure that you all know that when you have a triple bond, in the triple bond there is 1 sigma and 2 pi bonds, and in a double bond there is 1 sigma 1 pi bond. So when you talk of 2 pi bonds, that 2 pi bonds can be available in we have 2 carbon-carbon double bond repeated 2 times. So then it would have 2 pi bonds, or 1 triple bond. Now let us see one by one, and would show you. Here it is. So here, if I would say that if I talk of 2 double bonds, say for example, if I would say 2 carbon-carbon double bond, then also the degree of unsaturation is 2. So here I can do it like this. 2 double bonds can be generated like this, or can be generated like this. If I would generate it like this, this is 1 2 3 4. 1 and 2 is having 2 double bond, 1 and 2 is having 2 double bonds, so they are one and the same thing. Or you can generate it like this also, isn't it? You can generate it like this. Or is there any other way? If I would do it like this, 1 here, it got repeated, so there is no other way. And if somebody would do the carbon chain like this, 3 carbon and 1 methyl here, and if I do it like this, this also is a wrong one, because this carbon becomes pentavalent. So this means that these two, and the good part of the story is, once you have done 4 carbons you have attached, and in that 4 carbons you just have retained degree of unsaturation 2, then whether you add hydrogen or not, they would come out to be 6 only. Because if you just would add hydrogens here, just let me do for one, here you have 2 hydrogens, here you have 1, here you have 3, so 3 4 5 6. Here also, if you just would add 2 hydrogens here, 1 hydrogen here, 1 hydrogen here, 2 here, so it again becomes 6. So this particular compound can be available in these two forms. These two can be said as structural isomers. Now similarly, if I just would do in the form of one triple bond can also be possibly made here. So one triple bond can be drawn it like this, one triple bond can be like this. Is there any way other than this? No. So first and third are the same thing. So this got repeated. So here I can place a triple bond. No, this carbon would become pentavalent. So this would not be possible. So these are the two. Now the good part of the story is once you are able to understand this, because these four are the structural isomers which we generated from the 2 pi bonds. So 2 pi bonds when you have in a compound of C4H6, this is available in 4 forms. And all of these 4 are structural isomers to each other. Now, very soon we will be placing this in some classification. Just like these two would be, later on we will be saying this has to be position isomer. These also would be said as position isomer because the length of the carbon chain in these two are same. Only the position of double bond are changed. Or here also the length of the carbon chain is same. The position of triple bond is being changed. So that we will do in a minute's time. Similarly, if I would go for now one ring plus 1 pi bond, one ring, 1 pi bond, then also it also makes a degree of unsaturation 2. So the formula was C4H6. So here how can I do? So there is 4 carbons. These are the 4 carbon which I have attached, and so one ring is already being generated. So one ring means that there is 1 degree of unsaturation. So if I would place one double bond here, so this would become this one, C4H6. Now you can see it here. So there is 2 hydrogens here, 2 hydrogens here, 1 hydrogen here, 1 hydrogen here. So this happens to become C4H6. Similarly, if I would go further, so 3 carbon atoms in the ring makes the degree of unsaturation 1. Still we have to place one more carbon. So I can place 1 carbon here, 1 carbon here, 1 carbon here, 1 carbon here. And now in this formula, in these 4 formulas, we just have placed degree of unsaturation 1. We have to make it 2. So how can I make it 2? I just would place a double bond here and this becomes CH2. And similarly, if I can place a double bond here, I can place a double bond here, I can place a double bond here. So these two are same. Now very soon, so I can rub this one. So we have these as degree of unsaturation. So all these 4 compounds can later on would be said as to be structural isomers containing 1 ring and 1 pi bond. Now we have to place these in some classification. Very soon we will be saying these two would be said as position isomers because the position of double bond got changed or position of a methyl group got changed. So we will be doing it in the subsequent topic wherever it would come. Similarly, if I would go for this 2 rings, if I have to say 2 rings, I just have placed one. These are the 2 rings. Let me do it once more. So this is 2 rings we have generated, and if you would see, this is carbon, 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 carbon. How many hydrogens do we have? 2, 2, and 1 hydrogen here, 1 hydrogen here. So this happens to come under the category of bicyclo compounds. So we shall be saying this bicyclo and these are nothing but structural isomers, but these structural isomers would fall under the category of functional isomerism because this is bicyclo, this is cycloalkene. So this means we have generated lot many isomers of this. So this is the one we have just have done with. If I would hurriedly make all of these, so all of these there, if I have not missed anyone, so we said one is this, another is this, then we said about the triple bond, then this triple bond here, this, wow, and this one. So if I have not missed anyone, so all of these are the structural isomers of this compound, which later on we have to classify that in which category, because when you have to classify them into chain, position, function, and so on and so forth, so then they are said in with respect to each other. When I say these two would be said as functional isomers because this is diene and this is alkyne. Is it okay? So that thing we will be doing with respect to each other, that in what respect they are asking us. Okay, let me take one more example of C4H10O. Now, if I have to find the degree of unsaturation for this, the formula had been 2C plus 2 plus N minus H minus X upon 2. This is the formula. And in this formula, we don't have oxygen, and oxygen is not to be seen here. So the degree of unsaturation comes out to be plus 2. Nitrogen is not there, hydrogen is to be subtracted, that is 10 divided by, so degree of unsaturation came out to be 0. So this means that this compound degree of unsaturation is 0. That means there is no pi bond in this compound, and no pi bond and no ring in this compound. And you also have along with you oxygen. Oxygen always join with something either by one single bond or one double bond. And in one double bond, there is 1 pi, 1 sigma. Here you have 2 sigma. So this possibility is not there. So this oxygen, now this is beautiful. This oxygen is not joined to the carbon chain through double bond. So that possibility is not there. So carbon double bond oxygen is not possible here. Oxygen is not joined to this particular compound through the double bond. So now we have to dig deep into this, that how can I generate different structural allies C4H10O. So this is the beauty of degree of unsaturation. Once you happen to get degree of unsaturation 0, now you can simply do it like this. These are the 4 carbon atoms. If I would show it like this, these are the 4 carbon atoms, and you also have to join the oxygen. So I can join oxygen also with the single bonds like this. This you have to do the lot of practice, and with practice it would come. So now if I just would place hydrogen here, 1 and 2 are the same. So just to make it different, I just would take 1 carbon onto the side. So if I would place this carbon here, this first and second become different. Similarly, if I would do the similar thing here also, just hold on, here, if I just place a carbon here, so this also become different. Similarly, if I could do OH here and this one, this also become different. So all of these are alcohols, but somebody can do it keeping the oxygen in the center instead of at the corner, like OH. Here I can do it like this also. So there is another possibility, I can do it like this. There is another possibility, I can do something like this also. So all of these 7 isomers which we have generated would later on would be said as to be structural isomer, and they sooner or later we will be making them classified into different categories, just like 1, 2, 3, 4. So, and if I would say this is the longest carbon chain, 1, 2, 3, 4. So later on I will say these 2 are position isomers, because the position of function group got changed. Here the OH is on the second position, here is the OH is on the first position, keeping the length of the carbon chain same. And similarly, if I would say these two would later be said as to be chain isomers, because the position of the function group is same, but the length of the carbon chain got changed. So they would get classified into chain isomers. This would be classified into position isomer. And when you talk about these 2, so this is very important to understand fundamentally why we are classifying all these in different categories. So if I would classify these 2, if somebody would say this isomer is to be seen with this isomer, with respect to each other, these are functional isomers. Why they are functional isomers? Because on one side, on the left side you have alcohol, and on the right side you have a ether. So they would get classified under the category of functional isomers. So this is very, very important to understand. And very soon we will be saying, just like this one, here you have methyl and here you have propyl. Here it becomes isopropyl and this is methyl. So very soon we will be saying all these 3 are metamers to each other. So which would undergo in which classification is the understanding which we have to develop in the classification. I think I made my point clear, that with the understanding of degree of unsaturation, we are able to make different structures very speedily, knowing the fact that we have to keep pi bond or number of rings in any compound. Now let us hurriedly go into the discussion, and in today's session at least we would be able to cover first 2, chain and position, and rest we do in the next subsequent session. So when we talk of chain isomerism, Chain isomers are the isomers where the molecular formula is same, obviously because they are isomers, but different length of parent chain or side chain. When two, now make it a point, when this classification has to adopt, this is always with respect to the one which is being asked in the paper. So when I say chain isomers, the two isomers would, or two or three or four isomers would be said as to be chain isomers with each other when their parent length of the parent chain or the length of the side chain is different, keeping the position of function group same. Just like now, if I would say this is pentane, 5 carbon du 0. Here also 5 carbon du 0. Is it okay? So here the length is this alk is in this case is pentane. But for this it becomes 2-methyl butane. So this alk got changed. When the alk got changed, length of the carbon chain become different. Then these two would be said as to be chain isomers to each other. Let's take one more example. Just like if I would say 1, 2, 3, 4, 5. So here it is pent 1-ene. So position of double bond is first and alk is pent. If alk got changed, the length of the carbon chain got changed. 1, 2, 3, 4. So this 4, that means this is 3-methyl but 1-ene. The position of function group is still the same, but the length of carbon chain got changed. When the length of the carbon chain got changed, we would refer these two as to be the chain isomers. So while making the chain isomers, you have to keep this in mind that the length of the parent chain or the length of the side chain got changed, keeping the position same. Now somebody would ask that why not this? If you have a structure of this type, this definitely is a structural isomer of this compound. Du is say, because du in this all the three compounds is 1, keeping the carbon 5. So this also is a. Now here if I would say 1, 2, 3, 4. So 1, 2, 3, 4. So this, what is the name of this? This is 2-methyl but 1-ene. Now make it a point when I am talking with respect to this also is a chain isomer because the alk got changed from the pent. But when we compare these two, if I have to compare these two, you can say these as to be because here the methyl is at second position, here is in the third position, here it is in the second position. You can say it as to be position isomer as well when you are speaking these two with respect to each other. Otherwise, these three can be said as to be the chain isomers to each other. Now, similarly, if I would move for this particular compound, so it is 1, 2. So it is 1, 2 cyclohexane, and here it is 1 ethyl cyclohexane. Now the parent chain is same. Just concentrate on the fact the parent chain is same. Parent chain is of hex. Cyclohex. Here it is cyclohex. The parent chain is same, but the side chain length got different. So this is 1, 2, sorry, I missed it. 1, 2 dimethyl. So it was 1, 2 dimethyl, and here it is 1 ethyl. So these would be said as to be chain isomers. So chain isomers, if their parent length is same, but the side chain length got changed, they would also get classified into the category of chain isomer. Now, if just for comparison, if I have drawn this structure like this, this is 1, 1 dimethyl, 1, 1 dimethyl cyclohexane. So here the length of the parent chain. Now, if I have to speak this with this, if I have to compare these two, so here the methyl, meth and alk, cyclohex, methyl and cyclohex are same, but the position is 1, 1. So these would come under the category of position isomers. Fair enough. So I think I made my point clear. Very soon in the position isomer, we will be discussing it once again. Now again, if I have to talk about this two, so this is 1. So it is 1 ethyl cyclopropane, and here it is 1, 2 dimethyl cyclopropane. So cyclopropane, du is, by the way, we keep on writing the du also, because for the structural isomers du would always remain same. So it is 1, 2 1,2-dimethyl. So cyclopropane is same, but the length of the substituent chain got different. So these would fall under the category of chain isomers. I think I made my point clear that how is it to be placed the chain isomers. Now coming on to the first, let us discuss the position isomer as well. So what do we mean by position isomers? Position isomers of course would have the same molecular formula. Here the length of the carbon chain and length of the side chain carbon must be same. Only difference is because this type of isomerism would come into place when you bring in some functional group or multiple bond, or the subsequent position got changed. So they would have different position of functional group, multiple bonds, or multiple bonds means double or triple bond. Any double or triple bond position got changed, then it would categorize under the category of position isomers. But make it a point, while making position isomers, the length of the carbon chain, we shall be saying 2 or 3 or 4 compounds to be position isomers to each other when their length of the carbon chains is the same, only the position of function group, multiple bonds or subsequent got changed. So that is very, very important to remember. So here I categorically wrote it. While making position isomers, length of the carbon chain is not to be changed, while the position of function group of multiple bonds or subsequents can be changed. So that point you always have to keep it in mind. Let us do few questions. Just like if you have pentane 1-ol. So this pent would not change. You can change the position of OH group. So if I will place OH here, what does it become? It would become pentane 2-ol. So pent is still the same, but the position of function group got changed. Is it okay? Or pentane 3-ol. So pentane 3-ol. So these three would then be said as to be position isomers. So make it a point, I am saying it time and again, that the classification that which isomers are to be classified under which category would always be said with respect to each other. Similarly, if I would go for this 1, 2, 3, so it is 2 chloropropane, and the next one is also said as to be 1 chloropropane. Prop is same, 1, 2, 3. So prop is same in both this. The longest carbon chain is the same. Only the position of function group got changed. So they would get classified under the category of position isomer. Similarly, 1, 2, 3, 4, 5. If I would say this is 2-methyl pentane, and this is 1, 2, 3, 4, 5. This would become 3-methyl pentane. Then these would be said as to be position isomers to each other because the subsequent position got changed. Now here is a very interesting thing, that if I would have to write it, like say if I just would write hexane, because the degree of unsaturation here also is 0 with 6 carbons, C6H14. So if somebody would ask you, is 2-methyl pentane a chain isomer of hexane? Yes, it is. 3-methyl pentane is a chain isomer of hexane? Yes, it is, because the alk got changed. Here the alk is 6, here the alk is 5. So with respect to these two, these are chain. With respect to this one, this is chain isomer. But with respect to each other, they would be said as to be position isomer. So make it a point, position and chain isomers is to be done very carefully with respect to what they are asking. And similarly, if I would say this is pent 1-ene, 1, 2, 3, 4, 5, and similarly 1, 2, 3, 4, 5. So it is pent 2-ene. So what I did is position of function group got changed, keeping the length intact. Here it is also pent, here it is also pent. Now if I just would do it like this, say for example this. So these two would be said as to be chain isomers. These are said as to be chain isomer. Why? Because the position of the double bond is still the one, but the length of the longest carbon chain has become but 1-ene. So it is 3-methyl but 1-ene. So 3-methyl but 1-ene can be said as to be the chain isomer of pentane 1. So this is the point which you always have to keep it in mind. Now similarly, this is cyclohexane, and here it is 1,1-dimethyl. Now here what you are able to see, here it is 1,2-dimethyl, dimethyl cyclohexane. So here it is 1,3-dimethyl, here it is 1,4-dimethyl. So here all of these are position isomers, because the length of the subsequent, the length of the parent chain is not changed, only the position of the subsequent got changed. So these would get classified under the category of chain isomers. So this is very classified under the category of position isomers. So all of these are position isomers to each other. I think I made my point clear. So now let me add few things more into this. That if you talk of alkanes, first three members of alkane would not show any sort of isomerism, because this is CH4, this is CH3, CH3, and this is CH2, CH2, CH3, and Du for this is always 0. So there are 3 carbon atoms and you have to place the hydrogens. As soon as you just go for C4H10, C4H10 now can be placed in these two forms. One is the straight chain and another one is this one. So these are the 2 isomers, and these 2 isomers would then be said as to be chain isomers, because this is butane and this would be said as 2-methyl propane. 2-methyl propane. As a matter of fact, here is the very important point that always you have to remember, that for any alkane, when you are being given some, say for example this formula is given and they would ask you find the chain isomers, you have to make all the different forms which can be formed from a by any permutation combination, because the Du is 0. Here in this you have to be little attentive with that how the question is being framed. Just let me do it for C6H14. Now C6H14, as I already have spoken about on this, that first the 6-membered chain is made, open chain, straight chain has been formed, then 5-membered, and then I can make the 5-membered this way also. Now if I talk of these two, these can be referred to as position isomers. But if I would compare second with first, or second with first with third, these are said as to be chain isomers, but with respect to each other they can be said as position isomers, because now this is where you have to be very attentive with that how the fellow is asking. But other way around, when you talk of a alkane, alkanes would be having all the possibilities of alkane you can draw. All of them can be said, if the formula is being given, they can be referred to as the chain isomers. Now why is it so? Let me do it for you. Why I'm referring it like this? Because the fact here is that when somebody would say that write the chain isomers of this C6H14, so here we are not being given whether the starting material is this or this or this, or as a matter of fact the starting material is this, the starting compound is which one, or the starting compound is this. From where we have to start with, just like in some year back NEET examination, this type of equation came, that here if out of the 4 options you have to pick, then you have to compare always with the straight chain first. But this is not the right way to do it. The point here is, always remember it like this, that if C6H14 any alkane is being given, make all the possibilities can be referred to as chain isomers of each other, and among those chain isomers you can see some are acting as a position isomers as well. So that is the point which you always have to keep it in mind. Because why I'm referring all of these as to be chain isomer, principally we will say the open chain, straight chain is the basic one. With respect to that we are making all the isomers. So if this is hexane, if you have to change the, because this is the one, the other isomers of this alkane only would be found when you change the length of the carbon chain, and when the length of the carbon chain got changed, that would get classified under the category of chain isomer with respect to the open chain, open straight chain. Now let us dig deep into this. This is a very interesting point, that if you talk about C4H10, there are 2 isomers which we have drawn, 2-methyl propane and butane. Then for 5, if the alkane is having 5 carbon atoms, and similarly for hexane, it is 5 isomer which we have just drawn. And if you would you cannot do this in the exam. If in the exam from these alkanes you are being said to find the number of structural isomers, which is the general style of a question, here I would advise you to remember this: 8 9 18 35 75. So till decane you should remember this, that 2 3 5 9 18 35 75, starting from butane C4H10 ending with C10H22. So this you always have to remember. So these three you can, these 4 9 18 35 75 you should remember yourself. That is the good thing. And once you reach to the C14H82, if somebody would say that make the possible isomers of this particular compound, and if in case I say that 1 second is required for making one isomer, it would almost take more than 2 lakh years to make this come. So we cannot make it in our lifetime. So it is it 2 lakh? No, 20 lakh years. So almost this much years would be required to make all the possible isomers of this one, isn't it? So it is so interesting. This particular topic of isomerism is very, very interesting. In the subsequent session, we will now would be touching other forms of classification under the structural isomers. Today we have done about chain and position isomerism. Thanks a lot. Have a nice day. Stay safe and take good care of yourself.